network, or NLDN. Since the late 1980s, this network has been collecting the time and location of every strike in the United States. They estimate that between 20 million and 30 million strikes occur in the contiguous US each year. The reason for the spread in the numbers is that some strikes occur at the same time and are difficult to separate in the data. Lightning is detected with a vast network of instruments. Each sensor is sensitive to the large electromagnetic blast that is generated by each strike. Here's how it works. This map shows the location of all the sensors in the National Lightning Detection Network in the United States. Let's zoom in on one. If a lightning strike was to occur nearby, a large blast of electromagnetic energy radiates isotropically away from the lightning location. This blast radiates away at about 1/3 of the speed of light, and in a few moments passes over one of the sensors. The sensor records the time and exact moment that the blast of radiation passes over. When 3 or more sensors detect the same blast, the position of the strike can be triangulated. This works much in the same way as a GPS sensor works in your car. That is, for the position of your car to be found, at least 3 satellites must lock on to your GPS sensor to triangulate your position. The NLDN then maps the locations of the lightning strikes. The color coding represents the age of the strike. The strike position data have been used to make lightning flash density maps like this one. The color on this map represents the number of strikes per square kilometer per year. The number of strikes increases as you get closer to the Gulf of Mexico due to the conditions there that are warm, humid, and unstable for most of the year. Florida is the lightning capital of the United States. Some parts of Florida have over 100 days of thunderstorm activity each year. This map shows that parts of Central Florida have greater than 8 strikes per square kilometer per year. Now this map shows the flash density for the whole world. Your eye is likely drawn to Central Africa, where the flash density is greater than 50 strikes per square kilometer per year. Here in the heart of the African rainforest, thunderstorm activity is very frequent. Lightning in Canada tends to be concentrated along its southern border with the United States. This is because thunderstorm frequency decreases significantly with latitude in North America, as does the length of the warm season during which thunderstorms form. Furthermore, the farther north you go in North America, the farther removed you become from a large, warm body of water. Warm, humid conditions are needed to create frequent thunderstorms, and northern Canada rarely experiences this type of weather. In Europe, lightning activity tends to be concentrated around the Mediterranean and eastern Russia. Northern Europe's climate favors more stable atmospheric conditions, which inhibit frequent thunderstorm activity. Lightning strike frequency is much higher in northern Australia. This part of the country spends a significant amount of time each year near the stormy intertropical convergence zone. This is a zone of low air pressure, frequent rain and storms that kind of encircle the Earth near the equator. There is one location that is difficult to detect on this map that receives more lightning than any other place on Earth. In northern Venezuela, the Catatumbo River flows into Lake Maracaibo. The air above the mouth of this river destabilizes each day. The wind that flows across the lake, it will then converge and lift the air to create thunderstorms. This region experiences up to 160 nights per year with thunderstorm activity. Some storms last for 10 hours or more and produce hundreds of strikes per hour. So, how do clouds become electrified? Way back in 342 BC, Aristotle had been astutely observing that lightning and thunder were the byproduct of colliding air currents in clouds. What he didn't understand was electricity. It wasn't until the 1700s that scientists were able to create large sparks of electricity in the lab. The greater the charge and the longer the arc of electricity they produced, the louder the crack when the strike occurred. It wasn't until this time that we understood that lightning was an electrical event. In the mid-1700s, Benjamin Franklin is said to have performed his famous kite experiment, which allowed him to witness electrical discharge on a key tied to a string of a kite that he was flying in a thunderstorm. Now, if he actually did it, this was extremely dangerous and he was lucky that he did not get struck and killed. Franklin's scientific work, though, introduced us to terms that we still use today. He discovered that part of the basic science of electrical charge, and he defined charge centers according to their polarity and used terms like positive, negative, and neutral to describe their electrical properties. Many of us study this diagram of an atom. We know that atoms don't really look like this, but this conceptual model helps our understanding of charges. So here we go. Electrons carry a negative charge and orbit the nucleus of the atom. Protons carry a positive charge and combine with neutrons in the nucleus. If the number of electrons matches the number of protons, the atom is said to be neutral. An ion is an atom with too few or too many electrons. This is an important feature to remember as we learn about cloud electrification. Well, next, electrons are mobile. They can easily be stripped away from an atom. Protons are not as mobile. If they move, the whole atom moves too. We also remember that like charges repel and opposite charges attract. Electricity is a flow of electrons. An electric field is the attraction force between two charge centers when they're separated. The electric field is a line, positive to negative, and its strength is dependent on the size of the charge centers. Conductors are materials that contain movable charges. Good conductors are copper wire, silver, and gold. Water is a good conductor too. Insulators are materials that resist moving charges. Good insulators are made of glass or porcelain. Air is also a good insulator. Here is what the charge distribution looks like in a thunderstorm, just before the cloud produces a lightning strike. A positive charge center builds near the top of the cumulonimbus cloud, while negative charges accumulate near the bottom. In response to negative charge accumulating on the bottom of the cloud, positive charges tend to collect on tall ground objects, like the tree in this picture. What is interesting is that the ground and the tree were neutrally charged before the storm arrived. Remember that like charges repel. The negatively charged cloud base pushes the negative charges on the surface away, leaving a net positive charge on the tree. The electric field between the tree and the cloud can exceed 1,000,000 volts per meter. Now, just before the lightning strike occurs, the electric field reaches 3,000,000 volts per meter. When the electric field surpasses 3,000,000 volts per meter, dielectric breakdown occurs, which means that the air switches from being an insulator to being a conductor of electricity. This is one of the reasons why lightning is so powerful. It must pass through air, which is normally an excellent insulator. For air to become a conductor, the electric field must be enormous. If you are standing near the location of a potential lightning strike, you can feel the buildup of charge. Your skin will tingle and your hair will stand up on end. Have you ever been to a children's museum or a science museum and placed your hand on a Van de Graaff generator? After just a few minutes of touching this large metal sphere, your hair will stand on end. The Van de Graaff generator is a simple device. A rubber belt is turned by a motor, and a wire brush touches the belt and strips away electrons while it spins. The belt is connected to a metal sphere, and as the electrons are taken away, the metal sphere becomes positively charged. If you touch this sphere, electrons will be stripped away from your body too. Your hair, being lightweight, responds to the new positive charge your body now contains. Like charges repel, and each strand of hair begins to stand on end as they're repelled away from one another. The Van de Graaff generator is able to produce voltages similar to a lightning strike. You survive the experiment because the generator produces such high voltage at very low amperage. Lightning produces both lethal voltage and lethal amperage. So how does the cloud produce such a large electric field? There is one ingredient that must be present for a storm to produce lightning. You might be surprised to learn that without ice, a cloud cannot become electrified and cannot produce lightning. Ice can form in several different ways within a storm, but all ice crystals are six-sided at their molecular level. Individual ice crystals will grow in different shapes, and the majority of those shapes fall into a few primary categories. These shapes are called plates, columns, needles, and dendrites. These ice crystals have a large surface area compared to their mass and are easily lifted through the updraft of a thunderstorm. In contrast, other habits or species of ice form as supercooled water accretes onto the surface of an ice crystal. This process gives birth to graupel, which is a small, soft, spongy type of hail. Unlike the ice crystal, a piece of graupel has a small surface area compared to its mass, and therefore it falls through the updraft. The different types of